But yeah, it's really nice to see everybody here. And maybe just one thing, instead of choosing a chair for each session, I thought that maybe the most efficient would be that each speaker would be the chairperson for the next lecture. And there's a way to, there's this bell that we can be passed from speaker to speaker. But because we sort of need to start any induction in the base of the induction, Danny would be the base of the induction. So I think it's
my name is S.J. Dani, for those of you who may be new to this audience. It's a great pleasure to introduce Barak Weiss, whom I keep seeing at all these, so many of these meetings, and I'm sure he needs no introduction. The subject of Horocycle flows, which Hillel gave a big boost, and Marina made important contributions in whose name, in whose memory we are meeting here. And it's very fitting that Barak will be talking about the Horocycle. We're giving, in fact, a course, more than just talking, giving a course on the Horocycle flows. However, I should also emphasize that Barak has wide repertoire. I mean, it's not at each meeting I see him talking about various things and having many such meetings. So with this, I mean, the title, I suppose the speaker will announce the title. The speaker, I'm sorry, I didn't carry a prepared copy of the program. So enjoy the course. Thank you.
Thanks. Thank you very much. So thanks to, wow. צריך את הדבר הזה?
You need it so it could be recorded.
Okay.
So that's another thing I forgot to say for the speaker. One thing that you need to be aware of is that the institute would like to record your talk. So it will be discussed. But I mean, basically, if you're not asked for permission or not permission about recording yourself, forgive yourself. Ask about it.
Okay, so thank you everyone for coming. Thanks to the organizers for asking me to give this mini course. Thanks to Dani for embarrassing me in public. And let me tell you what this... הכל בסדר? זה פה, אבל זה עושה רעש. יותר מדי רעש. עכשיו? אוקיי. יותר טוב? בוא נתחיל אולי. אני לא יודע איך. אוקיי, נכון, יותר טוב. Okay, can everybody hear me? Good. Much better. Okay, so this is so Marina's famous works, which this is related to, are in homogeneous dynamics, which is a very symmetric and very beautiful space. And for those of you who are new to this kind of topic, basically what you should keep in mind is that there's a very beautiful, very symmetric space. And on this very beautiful, very symmetric space, the theorems say that all the orbits are nice, all the invariant measures are nice for a certain action. And the theme of my two lectures is about a certain other space where there's also a flow, or more precisely an SL2R action, where it had been thought for a long time that there might be a similar picture, and the similar picture is more complicated. So for the SL2R action, there's been a breakthrough set of results by Eskin Mirzakhani and Eskin Mirzakhani Mohammadi, and they show that for the SL2R action, all the orbits are nice, all the measures are nice. And there's another question for a one-parameter unipotent flow, And one may ask whether for this unipotent flow the same is true. And what I will tell you about today is that, in fact, it's not exactly true in the same way. More precisely, I will show you that orbit closures can be not as well behaved in this particular setting as in homogeneous dynamics. And the picture that we're going to get to at the end of the lecture today, I'm going to introduce this creature which we call a spiky fish, which is of course not an orbit closure in H11, but it's what we think of when we think about these particular examples. And so I want to gradually try to explain to you why we think this is a good metaphor for the type of creatures we're encountering. And so what I want to do in the first lecture is introduce the space, the action, and there's a lot of background which I won't assume that people know here about so-called translation surfaces, which are necessary just to get the discussion off the ground. It'll be kind of a crash course, and I'll focus exactly on the phenomena that are relevant to our examples. And in tomorrow's lecture, I will go into more detail about our examples. So today I'll just sort of set things up and state our results, and I'll also tell you about a very important phenomenon in this topic, which is phenomenon of flows which are minimal but not uniquely ergodic, which is kind of central in this domain. So we're discussing the space on which we're discussing is a space of translation surfaces. So let me define a translation surface. So vector A is an R tuple of natural numbers which sum up to an even number, and this even number I'll write as 2g minus 2. And with this data at hand, we can define something called a translation surface. A translation surface of type A is a surface M of genus G. G is this number solving this equation with a finite set of points, R points, where R is the length of this tuple, and an atlas of charts so the phi alpha are maps to the plane. And so they're equipping this surface with an additional structure, which is called the translation structure. And here's what we want to require on the overlaps. On the overlaps, you have translations. What this means now is that we're equipping the surface with every construction that you can make on the plane makes sense through these charts on the surface itself. In particular, we're going to be discussing flows along straight lines, one forms from the plane, and so on and so forth. The complement of these open sets is the entire surface except this finite singular set. And all the negative curvature is concentrated on this finite set, in the sense that at xi, the flat metric completes with a cone angle 2 pi ai plus 1. So in other words, when you have a regular point in the plane and you take a little small circle around it, you can measure the angle, and you see that the angle is 2 pi. And at these special points, they're not covered by these planar charts, but you can form a completion. And when you do that, you can still go around these loops and measure the angle. And when you do that, you find that there's an excess in the angle. The angle is no longer 2 pi. It's 2 pi plus an additional integer multiple of 2 pi. And this extra angle is captured by these numbers. Okay? So this one such creature is a translation surface, and we put all of these translation surfaces in a set for the moment. Later it's going to become a space, and these are all translation surfaces of type A. And we're going to act on this space by SL2R. It acts by post-composing charts, post-composition on charts. In other words, if we have one of these atlases of charts, we can get a new one in the following way. We take the same open sets, and then we map by phi alpha to the plane, and then we apply a linear map of the plane, and this gives us a new map. And you can now check that if the atlas originally satisfied these conditions, then so does this new atlas. Okay, so this is the notion of a translation surface, and there's a convenient way of presenting them in terms of polygons. So here is an example. So suppose you have, can people see these pictures or not in the back? Not really. Yeah, so these are, thank you. So two translation surfaces are considered equivalent if there's a homeomorphism between them which is translation in charts. Yeah. It's you can say the atlases are maximal if you like, or you can join them. Yeah. So there's two things to add here. You're right. So first, let's just talk about maximal atlases, and secondly, let's not just talk about all translation surfaces, but all translation surfaces up to isomorphism. The isomorphism is just when you have a homeomorphism that the translation in charts between two such objects, they're considered to be equivalent. And I think some people can't see, but some people can see these pictures, unfortunately. So what you do is when you have, so I'll just make another picture here, which I'm going to need anyway. So suppose you have some system of polygons, and you make some identifications on these polygons. So for example, maybe so I have a collection of polygons. On these polygons, I have pairs of edges of which are parallel and of equal length and opposite orientation. And then I just identify them. So here I'm identifying this side to this side. I'm identifying this side to this side to this side, and so on. Or in this picture, if you like, the edges here are all in different directions. There's only one way to pair them as pairs of sides of equal length, and you just pair them. So for example, this edge is paired with this one, and so on. This construction, what it gives you automatically is a oriented surface of some genus, and so that's where you get the surface. And the points here, which are marked in color here in black, are going to end up being singular points. I should have said points of sigma are called singularities. For example, in this picture, if I start going around this point, as I said, running around it and measuring the angle, here's what happens. I go around this point, then this edge is identified with this edge, so I end up here. I start going around this point, it turns out that I'm here. Keep going, and it turns out that I'm here. So far I've done 2 pi, but this side is identified to this side, so I keep going like that, and eventually I end up back where I started, and I've done a circle of 2 pi's worth. Okay? So in this picture, as well as in this picture, there are 2 cone points, each of total angle 4 pi, and so we live in the stratum H11, And if you can read from far away, we are now in this picture is an example of a structure in the space H11. Okay? And so these polygon pictures, you can say, are just a way of representing such a translation surface. And in fact, there's a bijection between objects that you can form in terms of these polygon pictures and this more geometrical definition of what they are. But when we think about pictures and polygons, the equivalence relation that we need to take into account is more complicated, and different surfaces can have, the same surface can have several different presentations. So here's an example of the same surface we had before, but it's been rearranged. Let's put it this way. How many people cannot see? The people who can't see, I don't want to be speaking to the empty set. So who are the people who cannot see these slides at all?
The pictures, not the text.
Oh, okay. Anyway, if you can see the pictures, that's fine. So imagine I take these two polygons and attach them along this long diagonal. Then what you're going to get is this picture on the left. So it's the same picture. It's just one polygon instead of two. And I've also added some intermediate lines to make it a union of triangles. And if I rearrange the triangles, but I always take care so that triangles are still identified to the same triangles they were identified to before, I can get another presentation. You see, for example, all the triangles in this side also appear on this side. This triangle over here is glued to this triangle over here. Therefore, this triangle is glued to this triangle, and so on. These are two different presentations of exactly the same surface. So if I'm presenting surfaces in terms of these polygons, there's a more complicated equivalence relation that I need to take into account, but these are equivalent notions. And in terms of these polygons, the SL2R action, which I wrote down over here abstractly, is much easier to understand. SL2R is just acting on the plane, so it maps, a linear transformation maps polygons to polygons, maps a system of polygons to a system of polygons, and so on. So that's the action that we want to study. Okay? And I want to tell you that this set of translation surfaces is not just a set. It's a nice space. It's called a stratum of translation surfaces. So let me write it over here. And it's going to be topologized. And I need to say something fairly precise about the topology. The topology is that this is a linear orbifold. So what that means is, ignoring the word orbifold for a moment, it's sort of similar to a translation surface itself in the sense that it itself, as an object, has an atlas of charts. And on this atlas of charts, here the overlap maps were translations. In this structure, the overlap maps will be linear transformations. And then it's an orbifold, which means that there are certain additional points where the manifold structure is quotiented out by a finite group, so you get some additional orbifold points. But kind of on a first approximation, it's a linear manifold, and linearity is important for our discussion. And let me kind of give you a sketch of proof of why this is true.
So is there an origin?
Pardon?
You said linear, not defined. Is there an origin?
So it turns out that there is an origin, except it's not in the space. Well, yeah, it's somewhat. I don't think that I've ever seen any advantage of this point of view. People call it an affine manifold, but strictly speaking, in the language of GX structure, you can take G to be a linear group rather than an affine group. I don't know if this has any advantages, but that's the fact. So maybe before saying the proof sketch, let me add one more notion. There's a map which I wanted to find. There's a map which I wanted to find by whole of M. Whole of M is an element of a certain cohomology group. And this will be important. So what is this object? So first of all, what is the first homology? The first cohomology of a surface? Well, first you think about the relative homology, which is just formal combinations of paths in M joining points of sigma. And then a cohomology, an relative cohomology are the linear functionals taking values in R2 on this creature up to coboundaries. Okay, so this is what I'm claiming, that whenever I have a translation surface, I naturally get a cohomology class of this type. And how do I get it? What I'm supposed to do is tell you how to integrate a path on the surface with endpoints in sigma or closed. And well, you can form an element of R2 just by taking the path integral on this path of the one forms dx and dy, which the surface inherits from the plane. We have planar structures, so it inherits in one form. So in terms of these flat pictures, if alpha, say, is the line, is the path going from here to here, I just integrate the x displacement and the y displacement along this path, and I get a vector in R2, and that's what the holonomy of the surface assigns to this path. Okay, so I have a mapping from surfaces into a certain cohomology group, and I want to show you why this mapping is actually a local homeomorphism, and how you can think of your stratum as being made up of pieces of this open sets in this cohomology space. So to understand that, you need to know that, yeah. It's well defined up to translations, and it turns out that the translations don't. Sorry, it's a well-defined vector. It's completely well-defined. Or maybe I didn't understand the question. Whenever you give me a path on one of these pictures that's a closed, a continuous path starting and ending at points of sigma, I can integrate it and get an element of R2 in a canonical way using the charts. Okay. So every fact, every translation surface has a triangulation tau into triangles with vertices in this singular set sigma. To convince you of this, take a look at the picture. You see right here that there's a translation surface and it's made up of triangles. Fact, you can always do this. I'm not going to prove this fact to you, but let's believe this fact. Now fix your triangulation, but don't think of this triangulation as an actual union of triangles with prescribed geometries. Just think of a topological thing. So think of a surface of a certain genus with certain marked points on it and certain segments on it which divide up the triangle into simply connected pieces with three sides. Okay, so this is called a topological triangulation of a surface. So fix some model S with a finite set sigma and a topological triangulation. Isomorphic to tau. Now, look at all the cohomology classes. Curly H sub tau is all cohomology classes which take R2 values that map all triangles to triangles in the plane with non-degenerate triangles in the plane with the correct orientation. Let me explain this condition. So whenever you have the cohomology classes such that all the triangles map to non-degenerate triangles in the plane, with the correct orientation. Okay? So when I have a cohomology class and I have 3 segments on a surface which form a loop, I can use the cohomology class to, I put one of these, I put a point at 0, and then I have a path on the surface. So here's my topological picture. And I have 3 curves on it, alpha 1, alpha 2, alpha 3. And now I put a point, I mark a point at the origin, I mark another point at beta of alpha 1, and I connect those 2 points by a line. So alpha 1 is assigned an element of R2 by the cohomology class. I do the same with alpha 2 starting here, and I get to a new point, and I mark that. And since this is a cohomology class, along the cycle it's going to vanish because it bounds a disk, so I'm going to end up here. So I get a triangle in the plane from this data, always. Now, the 2 things may happen. The triangle might be degenerate or non-degenerate, meaning degenerate means it has no area. If it has no area, I'm not in the set. The condition is violated. And if it has area, the orientation that I see in the plane might match the orientation that I'm given on the surface, or it might not. If it matches, I keep it. If not, I throw it out. In this way, there are finitely many triangles in triangulation. This is an open condition. In this way, I've specified for you an open set in cohomology. Okay? Now, whenever I'm in this open set, it prescribes a geometry to triangles. Once it prescribes a geometry to triangles, it gives me back a polygon picture, and it gives me back a translation surface, so it uniquely determines a translation surface structure with the right information. There's some information at the angles that I should add to this discussion, which I'm not writing down, but it should give me the correct angles at the singular points. Okay? So for every topological triangulation, there's some open set in cohomology, and this parameterizes all possible ways of putting geometries on these topological triangles to make translation surfaces out of them, of the right kind. And that's an open set in cohomology, and since different translation surfaces may have different presentations, this gives me a cover of this set, and the transition maps just correspond to changing the cohomologies, and you can check that this gives us a linear transformation. Sides of one triangle can be expressed as integral combinations of sides of another triangle. Okay, so this was kind of a very quick proof.
So are your angles always less than 5?
On each triangle, yes, this is the triangle in the plane. But the triangles have to, on the topological triangulation, there's some adjacencies, and you have to compute what happens when you run around an angle. And since they're all embedded in the plane, the angle that you get is an integer multiple of 2 pi. And if it's the right angle, the one prescribed by this data A, then I keep it. I just didn't write down. It's an additional condition here that I should have written down. It's an additional condition. So tau is given to me. It's an additional condition on the cohomology class. Yeah.
You mentioned integral coefficients, and so does that come from?
Yeah, and in fact, thank you. Yeah, that actually gives even an extra structure to this manifold. It becomes it has a preferred rational structure because the transition maps are in fact integral matrices.
So, but where do the integers come in the homology?
The homology,
Without coefficients.
you can think of this homology, right? You can think of this homology as being linear function mappings on this space with coefficients here. That's good enough, and the integers come from this. Okay, so I hope that was somewhat clear. And so we're equipping this object with a certain linear structure. And I needed to say that in order to state the breakthrough result of Eskin Mohammadi and Mirzakhani. I think I want to write it here. The dimension over the reals is 2g plus, okay, so the dimension over R of H of A is 2 times 2g plus R minus 1. let me subtract a 1 at the end. So this is the dimension of the homology space. We're doing R2 valued, so that's where this 2 comes from. And we can subtract a 1 here because we might want to always choose surfaces of area 1. So let's, from now on, restrict to surfaces of area 1. So that gives us this formula for the dimension. So in other words, the dimension can grow, and you get infinitely many examples with larger and larger dimensions. And on each of these spaces, you have an SL2R action, and that's the object of study. Okay. And so the so the theorem of Eskin-Rizakani-Mohammadi. I'm not stating it precisely. Stated imprecisely is for the action of SL2R, all orbit closures are nice, all invariant measures are nice, all stationary measures. Are nice. So apologize to the experts in the room for not being more formal than this. Actually, this is a trick I learned from Alex some years ago. I asked him, what's the conjecture for the Horocycle flow? This was a long time ago, and he said, the conjecture is that orbit closures are nice. So this is not a precise statement of anything, but if you want a more precise statement, what we can talk, let's ignore the measures for a moment, just talking about the orbit closures. The statement is that all the orbit in this linear structure, you can think about the notion of a linear submanifold. It's a submanifold that looks like a linear space in every chart. And the theorem is that the orbit closures are linear submanifolds, up to some issues with self-intersections. But I mean, as a first approximation, you can say all orbit closures are closed linear submanifolds. Okay, that's a very, very strong and important breakthrough of Alex Eskin, Martin Rizakani, and Amir Mohammadi. Okay, and now the question that we're asking is what happens for the Horocycle flow? The Horocycle flow is, before I talk about the Horocycle flow, let me just give an example of a submanifold that could be an orbit closure in the stratum H11, which is the stratum.
I'm sorry, your linear structures don't come from H1?
Yes, I take
And what's where's
the orbifold points. Let me answer your question in a second because it's coming up. H11 is the stratum of surfaces which have two singular points of cone angle 4 pi. So these are examples of surfaces in H11. And let me draw two more examples of surfaces in H11. Here's one. I take a torus, so opposite sides are identified. And I take another torus. Its opposite sides are identified. And in each of these tori, there's a line inside. And I think of this line as a slit. And so imagine cutting this slit and gluing the top side here to the bottom side here. So if you are on a path going from here, you don't jump over here, you jump over to the other side. Okay? If you work out what this means, it means that these 2 points, when you circle around them, you get a total cone angle of 4 pi. See, I'm going around, then I hit this line, and I jump over to the other side, hit the line again, and come back. And so this is a cone point of angle 4 pi. There's another one here of cone angle 4 pi. And the other points, the other corners here have cone angle 2 pi. Yes? Yeah, A is part of, A is an R tuple. That's why I have this line underneath it. It's a vector of length R. Oui? So this is an example of a surface in H11. And let me give you another example of a surface in H11. So this is example 1. This is example 2. Same combinatorics. The only difference is I chose my two tori to be identical tori when I started. So let's define by E, or sometimes E4. It's the subset of H11. Consisting of surfaces which can be presented as two identical tori glued along the slit. Okay, so this surface is in H11 because I've shown you how to make it out of two identical tori glued along the slit. Okay, and we're going to be seeing more examples. And this surface probably is not in H11 because it's not in E because these two toris are not identical. Of course, there might be another way of presenting the same surface as two identical tori, but if there isn't, then it's not in E. Okay, is the definition of E clear? E will play a major role in what comes later, and the reason for this 4 is just some kind of standard terminology. It's called the discriminant 4 eigenform locus, and this set clearly is SL2R invariant and closed. Right? I told you that SL2R just acts by linear transformation, so if I have such a presentation and I act on it, I still have a presentation of the same type. And it's also closed. Yes?
So what's my freedom in choosing elements of E? I can make those squares.
So thank you. So the dimension of E, let's do dimensions over here. The dimension, first let's do the dimension of H11. Okay? You can get the dimension of H11 from this formula, but let's just do this independently again. So this is a torus. The space of tori without normalizing the area has dimension 4. It's a quotient of GL2. So I get 4 degrees of freedom here. Another 4 degrees of freedom here. That's 8. This slit comes with 2 degrees of freedom because I can vary its length and its angle. So that's 10 degrees of freedom together. Minus 1 for the area. So the total dimension of H11 is 9. And the dimension of the eigenform locus,
when you rotate the slits, doesn't it cancel with some rotation of
the structure, if you rotate the structure, you don't get an isomorphic structure. No, I never said that. All the identification is up to translations. Rotations don't give you identical structures. Okay?
But you counted somehow. You counted the dimension in a way which seems wrong to me.
Why?
Because you counted GL2 dimension of GL2 degrees of freedom of choosing your
The two tori.
and then you added how many dimensions for the slit?
2 dimensions for the slit. I can place I can sort of decide where I want to the torus has this translation. All points look the same, so I just put this at my favorite point with no degrees of freedom, and then I have 2 degrees of freedom where I want to put the other point.
So here's my question. I know that rotation is not, things are not equivalent, but if I take those squares and I just rotate them, and I take the slits and I rotate them, I get the same object now.
No, you get a rotated object. Well, you can also rotate your head and then you're back, but if you don't do that. Okay, so the dimension of E, we have one torus which we're choosing. The second torus is identical to it. And everything else is the same, so the dimension is 4 times less, so it's a 5-dimensional object. So we have a certain 5-dimensional manifold sitting inside H11, which is this object E. It will play a major role in our discussion. It came up in the work of Eskin, Mirzakhani, Mohammadi as one possible orbit closure. Actually, the genus 2 case was done by McMullen before Eskin, Mirzakhani, and Mohammadi. So it's one of the manifolds that show up in the classification of SL2R orbit closures in H11. Okay, so this is just one example, but it will play a very important role in our discussion. Okay, so now we turn to our results. And this is all joint work with John Chaika and John Smiley. Yeah.
Are there any in the SL2 action this space, are there any non-trivial matrices that act trivially somewhere?
No. Maybe plus minus identity. It depends on some conventions, but in general, it's a locally free action. Locally free with stabilizers, maybe minus the identity in some. Oh, I wanted to answer your question about the orbifold points. This is an orbifold locus inside H11, and why is that? If you, since these two,
That's because of homeomorphisms.
yeah, there's a homeomorphism of this surface, which swaps these two. It's a non-trivial homeomorphism. It swaps these two identical tori.
So the singular, so the orbifold structure is because of the self-homomorphism.
Yeah, so there's a group of order 2 here, which fixes this structure. But in a neighborhood of it, if I make a small perturbation, I get to this structure, and the same homeomorphism does not act trivially. So you get some kind of orbifold subloci. So that screws around the tangent space at these points. It sort of divides it by 2, in a sense.
So the homeomorphisms also act on H1.
Pardon?
The homeomorphisms act on H1.
The homeomorphisms act on H1. They act on these actual surfaces. They act on H1. Everything is incompatible. Okay, so the theorem that we recently proved, which I'm going to be describing to you, is the following result. So let U be the upper triangular unipotent matrices. This is known as, this action of this group is so-called Horocycle flow. And one may ask whether, in analogy with Ratner's work, on this space, the orbit closures and invariant measures and so on, for this action, are as well behaved as the SL2R invariant orbit closures and so on? And the answer is no. There are surfaces in H11 for which, surfaces X in H11 for which the orbit closure under U has non-integer Hausdorff dimension. There are X which are not generic for any U invariant measure. So when you have a dynamical system with a measure, a point is called generic for it if, when you do Birkhoff averages along the orbit of that point, you converge to the measure. And what I'm telling you now is that you can find in H11 points which are not generic for any measure that you might think about. In fact, some of their Birkhoff averages fluctuate. Okay, that's the second item. First item is that there are orbit closures which have a fractal nature. So at least as far as orbit closures go, the picture is different from the SL2R picture.
Why can't we conclude from the first part that there are measures with calculation or measures which are spun?
Because it doesn't follow. You'll see. Maybe that's a good question to ask when I tell you the structure of the examples. But it doesn't formally follow in any way. Pardon? Oh, yeah. I didn't.
In the theorem by Estin and Homology, there is not, like in the homogeneous setting, any equivalence between these different, you said different objects are nice.
There is an equivalence. There is an equivalence. I didn't write it. Every point which belongs to the support of any measure and is not in the support of a measure not contained in the support of a measure whose support has smaller dimensions. Supports all have dimensions. All points are generic for one of these measures. And so the points actually determine the measures. All points generic. That's actually, if you know a little bit about the distinction between stationary measures and invariant measures, we're acting with a non-amenable group, SL2R. You really need to understand all the stationary measures in order to make this conclusion, which is a very, very strong conclusion. All points are generic for one of the measures. I'm not telling you what generic exactly means when we're discussing an SL2R action. You have to average in some way along SL2R orbits, but this is a very strong conclusion. Okay? So the situation is different, at least as far as orbit closures go. situation is quite different. Now, yes? All we know about the Harsdorff dimension at the moment is that it's somewhere between 5.5 and 6, and strictly less than 6, and we don't know the number. And this is a lot of this is still being. It's hard to compute the actual Hausdorff dimension.
When you say the Hausdorff dimension between 5.5 and 6, one set that's bad, or?
No, I'm stating this in H11. This can be done in lots of other strata. It's all other strata, which except we don't know how to do the smallest one, which is H2. But I'm sure.
In H11, is there one bad set?
No. We have plenty of them. I'm not stating the results in full generality. It's easiest to work with this particular creature as some building block, and I'm going to present to you one orbit closure or some orbit closures which are sort of associated with this. Near 1? I have no, a priori I would say probably no. Well, of course we have periodic orbits. I would guess the answer is no, but I don't want to, I don't know. Certainly our examples are not like that.
You say you invariant measure, you improbability measure?
Yeah.
Is there non-escape of mass?
There is non-escape of mass in this whole topic. That's been proved a while ago. There is some kind of analog of both the Eskin-Margulis-Moses type of non-divergence results and the Dani-Margulis non-divergence results for these whole unipotent flows. Okay, so let me tell you one of the main mechanisms for our proof, and if you've sort of not been following, now I'm going to talk about something that's on the face of it completely different, so it's a good time to catch up. And this is about the existence of surfaces on which the straight line flow is minimal but not uniquely ergodic. So minimal, non-uniquely ergodic straight line flows. So this is not the Horocycle flow, it's a straight line flow. What is a straight line flow? Whenever you have an object like this, you can choose a direction, say the vertical direction, and you can start moving in the vertical direction respecting the side identifications, and you wrap around the surface in some way. And if you like, you can think about a torus. The easiest example is a torus. And if your direction is irrational with respect to the torus, you're going to be minimal and also uniquely ergodic, and otherwise you're going to be periodic. So there's a kind of a dichotomy for tori, but for higher genus surfaces it was discovered in the 70s, and this is a topic which has attracted really a lot of work and a lot of attention, that, and I don't want to mention names because I would end up offending people, but a lot of people were involved, that there are examples which are minimal, so all orbits are dense, but they're not uniquely ergodic, so they admit more than one invariant measure. On all of these structures, the Lebesgue measure is always an invariant measure, and the question is whether there's another additional measure which is invariant. Okay? And I want to, and the answer is yes, there are such examples in genus 2 and higher, and I want to show you how one constructs such examples in the E4 locus. Okay? Let's construct examples. By pictures in this locus. And this is a construction following Veitch, Maser, Smiley. So basically, Veitch did this in the 70s. Maser and Smiley gave this a geometric interpretation in the 80s. And I'm going to give this a slightly new twist here. And so we need to first understand something which I call a checkerboard pattern. What's a checkerboard pattern? I take a torus. This square has opposite sides identified, so it's a torus. And I put two lines on this torus. And they have the same endpoints. The first line is this horizontal segment from here to here. And the second line is this long diagonal wrapping around the thing, and it starts here and it ends here. Okay? And these two lines subdivide the torus into lots of connected components, and I choose my lines in such a way that I can color the regions colors so that adjacent regions have different colors, in two colors, red and white. So it's not always the case that you can make a coloring like this, but let's assume that you can, and in fact you can. And now let me tell you a fact, which you might take as a good exercise. It's an interesting exercise. And the exercise is the following. What you're supposed to see in this picture is that there's more white than red. The coloring is not 50-50. There's more white than red. And so here's the exercise. Show that you can construct such examples where the long line is fixed and the long line varies, making the long line converge to any prescribed angle, and making the proportion of white to red converge to any prescribed number between 0 and 1. So let me say that again. I can find a sequence for any direction which I want, say the 45-degree angle. I can find a sequence of such examples where the long line is getting longer and longer and longer, and the direction of the long line is approaching my favorite direction.
What is it that you fix?
I fix the short line, and I fix the torus. It's a property of the short line. I'm telling you that I can choose my short line. The short line should be irrational in some sense, but that's all. There's a simple condition on the short line. And now the property of it is that if you tell me any preferred angle, say 45 degrees, and any preferred proportion, say 83% is your favorite proportion, you can find a sequence of such examples where the long line has direction approaching 45 degrees and the proportion of white approaches 83%. Okay, that's a fact which you can take as an exercise.
Lines will not converge.
The short line is fixed, so of course it's converging, and the long line is converging in direction. That's all I'm saying. It's getting longer and longer. Its length will not converge. Its length will get longer and longer. Okay, suppose you've been able to solve that, and now what I want you to do is take such a picture and draw it twice with colors flipped. Okay? So this is one such picture, and this is the same picture except the roles of the color have been reversed. And let's think of this surface, and let's think of the gluing along the slits that I mentioned before. Okay? What have I constructed for you? I've constructed for you a surface of genus 2 in my locus E. Right here it is. It's two identical tori glued along a slit. Where's the slit? Well, here's the slit, if you like. But actually, no, there's another slit here. The long line is also a slit. So it's the same surface exhibited as a union of two identical tori in two different ways. Okay? In my first way of exhibiting it, the left-hand side is one torus, the right-hand side is another torus, and the slit is the short segment. In my second way of presenting the same surface, the red part is a torus, the white part is another torus, and is very, very long and stretched, and the slit is this line. How do I know? Well, just take all the red pieces and add them up. You get the same torus that you had before. So it does project 2-to-1 onto a torus. And the only way to get from red to white is to cross this. When I cross the non-horizontal line, I go from one connected component to the other. Okay, great. So I've found surfaces of genus 2 in this E4 locus with this imbalance in the way that the colors are proportioned. Okay, now I'm going to define a measure for you on this picture, and the measure is Lebesgue measure restricted to the red region. What do we know about Lebesgue measure restricted to the red region? Well, it's Lebesgue measure on one torus. So it's invariant under moving in the direction of the torus. So if I take a point here and move it in the direction of the red lines, the measure is invariant under that transformation. Okay? So it's a measure. And I do this again and again and again for more and more of these examples. And I get a sequence of measures, and by weak star compactness, they converge to something. What do they converge to? They converge to some measure which is invariant under what? It's invariant under the flow in the limiting direction. So the flow in the limiting direction will have an invariant measure, and this invariant measure gives more mass to the right-hand side than it does to the left-hand side. By the picture, it's giving all the red. You see more red on the right-hand side than on the left-hand side. So in the limit, we found another measure which is invariant under the straight line flow in the red direction, and it's not Lebesgue, clearly not Lebesgue, okay? And I have enough freedom in this discussion. I can make this happen so that my limiting direction is any direction. I can make that limiting direction a minimal direction. All but countably many of my directions are minimal. So by combining all of this, I get an example of a surface which is minimal but not uniquely ergodic. Okay? Now let me quickly introduce my... Elon, what's my time right now? So I have 5 minutes? Sorry, you're the boss now. So let me... This is a construction on one flat surface. I said people who fell asleep can wake up. The moduli space for this discussion is gone. It's a way of constructing one flat surface with a minimal non-uniquely ergodic foliation. Okay, take all the red and think about how you cross from red to white. Now, if you when I go from on this piece and I hit the white-black line, it glues to this piece here. So when I do that, I don't move off of red. My only way of going from red to white is to cross the diagonal line, right? So the red is one connected component for the complement of the diagonal line. So the diagonal line also breaks up this surface into two connected components. They're both tori. In this picture, they're very complicated tori. But in fact, it's clear that you can assemble the original torus from them because you just merge all things of the same color. So I've presented the same surface to you. I mean, what's completely clear is that the white torus you see in this way and the red torus you see in this way are isometric, right? And so I presented the same surface to you in two different ways as a union of two tori glued along the slit. And what the imbalance here is the imbalance of how one torus decomposition intersects the other torus decomposition. Okay, now fact or theorem. This is, there's a lot of people, so theorem. And this is a particular theorem that I'm quoting now is due to Chung, Hubert, and Maser. Let's talk about the set omega, which is x in E, such that the horizontal direction on x is not uniquely ergodic and minimal. Then the dimension, Hausdorff dimension of omega is 4.5. So the measure of E was 5, and the Hausdorff dimension of this set is 4.5. So it's some kind of a fractal object.
Minus what E was?
E is the all the surfaces which can be presented as two identical tori glued along the slit. And now I'm going to sort of give you an explanation of what our result is about. So let me draw a picture first, which is very schematic, and then I'll show that fish again. So imagine that we have this set E. We're at H11. Okay? This is the set E. It has dimension 5, and so you're seeing one dimension of it in a higher dimensional space. H11 has dimension 9. I'm showing it as the board as a two-dimensional space. And on E, there's a subset omega, which is some fractal set of dimension 4.5. It's not close, it's dense, in fact. And I'm going to draw some lines starting at this set. Now these lines, on my picture, the lines are always going in the same direction, but that's because I don't have enough space. Think of these lines as pointing in one-dimensional lines, poking in potentially with 2 degrees of freedom. So in a 2-dimensional set of allowed directions. So these lines are sort of poking out, and there's an extra 1 dimension of angle, and you don't know, each line can poke in a different angle. Okay? That's the structure of the object that we're constructing, and so the orbit closure, whose Hausdorff dimension is between 5.5 and 6, just is a union of such lines, starting at all the uniquely ergodic the non-uniquely ergodic surfaces in E, poking out a fixed distance A. We can find one orbit which picks up all of these guys in its closure. The lines are, I'm going to tell you how to construct them tomorrow, but the lines are just one-dimensional lines of surfaces which start at these non-uniquely ergodic surfaces and go out of this E4 locus in some direction which is in a 2-dimensional plane. And the length of all these lines is the same. Of course, now I have to tell you what I mean by length. There's a length measurement which assigns them all the same length. Yes. This is the orbit closure with the orbit. The orbit is in here, but it's a 5-dimensional. So the orbit is going in whenever it sort of goes in this direction. Remember, this E is 5-dimensional. This set is also Horocycle invariant. So anyway, the thing is, just imagine the flow going this way. When it comes back somewhere else, and so on and so forth. So that's the orbit closure. So maybe now you agree with me that this is called a spiky fish. Maybe you don't. Some of my co-authors also don't agree, but they're not here, so I took the opportunity. So to me, this is a perfect picture of this. So whenever we show this fish, just to make it clear, whenever we show this fish, there's kind of like a smooth, shiny thing inside the fish that you can believe would be there if you scraped off all the spikes. And that's, for us, is this locus E. And then there are all these spikes which are based at the non-uniquely ergodic set. And you're supposed, here they look kind of regular, but you're supposed to imagine that they point in kind of very mysterious directions. Okay, and just one more teaser for tomorrow's lecture. What the pictures that I showed concerning the imbalance, this checkerboard pattern with the imbalance of colorings, is exactly the mechanism which allows us to control where the orbit is going in these spikes. So there's a kind of a length parameter along these spikes. The orbit is going to run around here in some way, and we're going to want to force it to come close to each and every one of these spikes. And in order to do that, we have to analyze those checkerboard pictures that I showed you a few minutes ago. Okay, so thank you very much for your attention.
Any quick questions?
Yeah.
You said E is 5-dimensional and H11 is 9-dimensional.
Yeah.
So why are there 2 dimensions of freedom for the lines from omega?
So if you know this homology space, there's the real directions and the imaginary directions. So the codimension is 4, and inside it's not just codimension. There's kind of a natural complement to the E4 locus, which is 4-dimensional. You can pick out in terms of, say, a symplectic form. There's a kind of a natural 4-dimensional direction, and you cut down the dimension in 2 because this 4-dimensional space has so-called real directions and imaginary directions, and the real directions there have dimension 2. So that's where the action takes place. Yes.
Omega is density.
Yes.
So with that, let's thank Barak for the nice presentation, and we will of course continue tomorrow.